it is a damn good feeling to be here, actually, and be able to talk to people. Thank you, Czesław, for the introduction. Thanks, Borivoje. Thanks, everyone, for organizing this. One of the things that will be remembered is probably by many of us, first post-pandemic conference, where you can actually go and see people. It's amazing to be here without masks and all that. Thank you very much for inviting me, giving me this opportunity to say a few words about these topics of mediators and gravitational entanglement, some works of us that go together with the theme of this conference, which is asking this kind of questions. Does gravity admit non-classical features? If so, which ones? And how many more generations of physicists do we need to finally detect them? So yeah, I guess I'll just, since I was assigned this first kind of spot, so I'll start a bit more generally than perhaps necessary. So obviously this was addressed a lot by many people, both theoretically, experimentally. On theoretical side, we have the field of quantum gravity with many different approaches. Some of them will be covered in this conference. Very much looking forward to the talk by Carlo Loverli about loop quantum gravity. Essentially, I'll not really talk about this. I just gathered here this reference where Matt Lake kind of has literature or gathered literature about these different topics. The question I'm going to ask is more pragmatic. Just what do we actually know about this quantum and gravity border from experiments? So here's a selection of beautiful experiments where quantum particles move in gravitational fields. And let me just say a few words on the first one, and then all of them are in essence very similar, but just to stress that there is really some nice quantum mechanics going on. So what we know is that small stuff falls in gravity just like big stuff does, but it's funny when it falls, say, on a mirror. A mirror is a material which you cannot penetrate. So imagine you have a mirror which is just horizontal, and you have a neutron and it falls, so it will kind of bounce. You would think, like this is what big particles will do. So from neutron's point of view, this mirror is something that it cannot go to. So it sees it as a gigantic potential. It's like infinite potential along this direction. And on top of this you have gravity, which is linear, so that's kind of just linear mg height, then the net result is this triangular well, which is confining and it has discrete energy levels. So that's exactly what this experiment is showing, that neutrons that fall on a mirror in gravity do somehow, you can observe this discrete energy levels. Quantum mechanics, really. So of course, the famous Cow experiment, if we have matter waves interferometers which have arms at two different heights, there you can see this gravitational phase shift in their output. Atomic gravimeters use atoms to estimate gravitational fields. Gravitational redshift has been observed. Atomic clocks tick differently at different heights. More recently, people have observed phase shifts kind of on some macroscopic wave functions that depend on space-time curvature. So, are these guys evidence for quantum gravity? Clearly, there has been some quantum effects here. And you probably already see from these labels, the classical labels that I have given here, that I'll argue for no. And really, the basic physics is just this, that all of these experiments, they have a common element, and that's Mother Earth. Essentially, we're talking about the very tiny objects with the tiny gravitational fields that move in this gravity of the Earth, so practically without disturbing it. So you could effectively think, practically speaking, it's very hard to detect those back actions. Effectively, there is no back action on Earth's gravity from quantum particles in these experiments. Or in other words, we could embed this description of this experiment into quantum formalism using just one state for gravity. And I'll do that in the next slide just to emphasize kind of where, and it will allow me to easily go to where I want to go. So here I just want to stress that, obviously you can question that. This is probably not really the good way. It's not obvious whether you can really embed gravitational experiments into Hilbert spaces or whatever, this standard quantum formalism. One should think about other ways, perhaps some really full-flavored quantum gravity or post-quantum models, and people have looked into that, right? Like John Selby, who's here, Chiara Marlette, and so on. So here's my toil model, just to stress. So I will stick to this embedding into quantum formalism because it will lead to some very simple notion of non-classicality that hopefully I'll be able to communicate. So here's the toy model. So imagine you have this neutron or something, some massive particle that in the surface, next to the surface of the Earth. So obviously, no one will question that you should use a Hilbert space to describe this neutron. But now I will also write a Hilbert space to describe this arrangement, arrangement of the gravitational field. So say next to the surface of the Earth, we have these different accelerations, and I'll just assign some ket G to this. If this was next to the surface of the moon, that would be another G, which is in Hilbert space orthogonal to this one, and so on, right? And now when I write the coupling between this particle and the field, I'll just introduce explicitly this kind of splitting and introduce some operator G for the gravity. And since it's practically doesn't change this experiment, I can choose this G ket to be the eigenstate of G, returning this as eigenvalue, gravitational acceleration. And in such a toy model, you immediately see that when you start with the particle in state psi 0 and gravitational field in this state G, it will evolve in time in such a way so that G decouples, and that's the one and only state that I need here to describe this experiment in that Hilbert space. And the particle evolves under this MGH or MGZ potential that all of these Newtonian experiments are using for their explanation. So, two conclusions from this. One, in order to somehow be able to move beyond this situation where I have only one state for G, it would be great to have experiments with two objects of similar size and sufficient mass for both of them to influence gravitational field. So in this embedding, I'm really looking into this kind of scenarios where I have two objects that interact through the third object. And hopefully there will be such that I cannot just separate this, right? Exactly. So, and this is my second observation, that where I'm going is it would be great to have a method which will tell me just from observing dynamics of AB without ever touching C, because this is supposed to describe this gravity. So we don't really know exactly how we should do that. So I want to make minimalistic assumption about this mediator C. I don't want to know its Hilbert space dimension. I don't want to know exact form of these interactions, and yet be able to conclude by just observing KB that something non-classical is going on C or this mediator. Actually, I think we can also, if some of you have questions in the meantime, I'm happy to answer them also on the way, right? So here's my notion of non-classicality. So where I'm really going for, of course, it would be great to have a method that shows you that not only one state of this mediating Hilbert space is used by more, but I will demand even more than that, that I don't want them to be orthogonal. So in other words, we would like to have a method where just from looking at AB, we would like to make conclusions that the whole tripartite state is not of this form where C's are orthogonal. So when I say classical, once again, this means that a system is in, or maybe correlated to other systems, but it is sufficient to use just one basis for its description. So I could measure this system along this basis without disturbing the whole multipartite state. That's the that's the classicality notion. Measuring without disturbing, or dephasing without changing the whole state. And these states, they are known. So in literature on this quantum information community, this kind of the states which are not of this form are called to have, they're said to have quantum discord. So in quantum info language, I'm looking for a method which will tell me by looking at AB, so at particles that are interacting via mediator, that there is some discord on this mediator. But I don't want to touch the mediator. And you can already from here, you can if you have this quantum info picture, you can kind of see how one could do that, because these states of that form are also models of classical communication. That's exactly what we mean when we say that we classically communicate, that the particles that we exchange are in one of some distinguishable states. So the idea at first sight is, why don't we just look at entanglement between AB, and that probably will tell us whether the only way to entangle A and B is when we have this discord as would be measured on C. And that has been formalized within quantum formalism in this paper. And we have derived conditions there for entanglement to grow in these mediator scenarios. I'll show you them later, but at the moment, of course, I have to mention the BMV experiments, the papers by Chiara Vlatko and Bose and others, which have essentially the same idea, where you have two particles or two masses, but prepared in some specific initial state. They interact gravitationally, and from entanglement gain, you conclude that you have some quantum features of this mediator, or here gravity. So one of the things that I wanted to stress here is that it's not enough to just look at entanglement gain. You actually have to add some information to this whole picture. And here's a simple example. Why do you have to add some information? So in this example, the particles AB start unentangled, and they get entangled, and I will argue that via classical mediator. How does that happen? Well, that's possible only when you actually have some entanglement initially. And in this example, it is this kind of entanglement between one object and two of them together. So imagine you have this initial state. So some maximally entangled state between the two particles, AB, correlated classically, admittedly, to this some state of C, and some other maximally entangled state correlated to the minus state. So when you trace out the C, this thing is not entangled. As one can prove, maybe it's not so obvious when you look at it, and you're not from the quantum info community, but one can prove that indeed this is the case. At time zero, this state admits no entanglement. And now imagine that I choose this interaction Hamiltonians, which have the form AC plus BC, so really mediating interaction Hamiltonians, in such a way that it's actually the states of particle C are eigenstates of this Hamiltonian. They never ever evolved. They are stationary states. So at all times, this dynamics is somehow of this form. It will always have a plus state for C and a minus state for C. Only these states between AB will change. And you can prove that actually, in such a way, entanglement between AB does grow. And it turns out that there is a moment of time where this state evolves to certain maximally entangled state, which is the same as the state evolved from this phi plus. So you can even get maximal entanglement in this way. And I stress again that C is in the mixture of plus and minus, so you could measure it. You could continuously in time dephase this C, and yet you would in principle, let's say, see the entanglement grow between A and B. And that's exactly what people have observed in the spoon experiment with NMR. So they just took that example and kept on dephasing C experimentally, and yet they observed that this entanglement can grow. So I'm just stressing that, you should be careful, and some information has to be added. It's not just about entanglement gain, but you have to look at the properties of your initial state as well. So, by the way, it's neat. So in their molecule that these NMR people are using, it's very nice how this mediator scheme is realized. So this is the bond structure, and you can clearly see that carbon mediates interactions between H and F. So, yeah, and such a method, we have derived in this 2017 paper, and it turns out that if you observe at time t that your entanglement is greater than the sum of initial entropies of these particles A and B, then you conclude that you had somewhere at some time during this evolution, there must have been quantum discord as measured on C. So some non-orthogonality must be involved in this description of C when you embed it in Hilbert space. Quantum coherence, in other words, right? And I'm stressing again that so independently of this gravity, right? This is actually, if you're experimentalist, this is the inequality you should be interested in, and you would like to do this experiment. So don't just look at entanglement gain, right? But you really prove that this holds, right? Then you have this conclusion. And importantly, and this is completely independent of gravity, but just generally speaking, good to know for any system which has mediators, that this conclusion holds under minimalistic assumptions about this mediator. So no fixed Hilbert space dimensions. You don't have to know the form of interaction Hamiltonians. Actually, each of the systems A, B, and C is also allowed to be open to its local environment, but not a global one, because then you could entangle it via some common environment. But if each one of them is just open to a local environment, that's just fine. And again, no knowledge of initial state. That's the end of part one. I wanted to arrive at this inequality. So at the end of the day, and you see that in good experiments, actually this entropies will probably people will prepare states close to pure states. So this entropies will be close to zero. So essentially it's all about getting entanglement. So the second part, how do we actually, what are the experimental conditions to actually produce such entanglement in the lab? And we'll look into optomechanical experiments. I'm very happy that Marcus is here. So yeah, maybe this is somehow useful. It's all based, or majority of this is based on the paper with Tanjung Krisnanda, Guo Tam, and Mauro Paternostro. So we were looking at this kind of stuff, actually two setups, but let's take a look at the first one, which is really optomechanics. Imagine you have two masses and each one of them is in some harmonic trap. You cool them down close to ground states, then you turn off those cooling lasers. That's kind of in imagination of theorists how these experiments look like, right? You first cool them down, then you turn off your lasers, you let them interact via gravity plus some noise that you have in the lab, probe entanglement at a later time. So where does this lead us? What are the conditions? And now, before I show you some calculations, there's one intuitive kind of just argument that will show you immediately what's the relevant figure of merit here. So when you look into the gravitational coupling given by the Newtonian potential between the two particles, here I have the following notation, that L is the distance between the centers of mass A and mass B, and XA and XB are displacements from equilibrium. When you cool down, this XA and XB are small numbers. They are, on the order of ground state extension, very small numbers, definitely much smaller than L. So it makes sense to expand in this parameter that the displacements divided by L. And you see that the possibility of entanglement emerges in this second order term. This one is just some energy shift. The second one is local. Only this one is actually coupling the systems. One immediately sees that probably such experiments will be time consuming. They will take a lot of time. And second, here's the intuition that one can expect that in order to generate appreciable entanglement, let me just read it, the last term, so the one that couples the two systems, it would be good if it's comparable to the energy of each oscillator, because if this is not the case, it's mainly free evolution, with some very weak coupling, and you have to wait even longer. So that's a kind of natural expectation that the coupling term is comparable to the energy of each oscillator. So the coupling term was this square stuff divided by L cube. That's this one, right? And now I'm just dividing by H bar omega. And if these oscillators are close to ground states, and we replace this displacements by ground state extension, we arrive at the quantity that turns out to be the figure of merit here in this experiment. So it's a combination of GM omega divided by omega squared and distance cubed. And why is this relevant? Because this number actually sets the precision of entanglement detection that you need in your experiment. And you can see it as follows. So I even have the frame for this important parameter. And if you start this whole dynamics in a thermal state, it turns out that the maximum entanglement you can get is exactly this number eta that I have just obtained in this intuitive way. And if this, and there's some correction that comes from thermal excitation. So this is a mean number of phonons in this oscillator. So this is the maximum entanglement you can get. So you have to be able to measure with this precision. Otherwise, you can't see it. And it helps actually in this form of experiments to have squeezing, because then this parameter eta is just replaced by the sum of squeezing parameters. So let me just give you an example why this is important. So obviously it's a minus. So temperature kills entanglement, no news, right? This we all know. But it's really really a killer, right? So for this eta, which is setting the entanglement precision, if you choose it to be 1/100, which is what people have realized with some optomechanics experiments, then it will show you that you would have to cool your oscillators really hardly, right, to this occupation number 5 in 1,000. And with squeezing, you can go to up to 14, so it's really important. And that's also the squeezing parameter, which people have already realized in some optics experiments. Yeah, so is this feasible? It's easier to see if we replace mass with density. Density doesn't change that much for natural materials. So if we put these two masses at the distance 2.1 radiuses and replace in eta mass with mass density, we get the following expression. And the densest naturally occurring material is osmium. So if you use this osmium, then and choose this entanglement resolution that has been achieved, it requires oscillators that are slow, that go with the frequency which is 1/100. So it's even hard to say how would that exactly look like, and how do we cool down such slow oscillators? And actually, so there has been tremendous progress in this, surprisingly, by the LIGO community, which recently managed to cool down almost to the ground state oscillator with frequency 0.43 Hertz. So this sounds like one way to go, but actually, if you also include the noises such as Brownian noise and the stuff that you have there, it turns out that these experiments would require about an hour to get entanglement of the order 0.01. So they are too demanding, too high mass, too low temperatures. They are too slow. We need a new idea. And this new idea, so I have one more setup to present you. And this new idea is kind of coming from the following intuition that here, so when you think, where does this entanglement actually come from? So when you have two masses and each one of them starts in some Gaussian state, so it's supposed to be a Gaussian, then those parts of a Gaussian that are closer, they interact more gravitationally than those that are further apart. So soon after, they will move faster than the ones that are further apart. And this space momentum correlations are somehow the source of entanglement. So if you think like this, it makes sense to actually switch off those harmonic traps, because then you have free evolution and the wave packet can expand much more. And that actually, so the idea is to release the masses, and that turns out to be working pretty well. So just to have something concrete in mind, right, or the timescales which would be of interest here. If you think about this drop tower in Bremen, right, it has a free fall time in the order of 4.7 seconds. So it would be great to achieve entanglement by switching off the traps within a second, let's say. That's perhaps could be done in this sort of experiments. So this is the final setup, that at some height, right, we first keep these masses in their traps, we cool them down, then we release them, or another option is that in principle this could be in space, let them go, and after some time measure, estimate entanglement. And it turns out that with these osmium spheres, right, you can design much more microscopic parameters where you do achieve entanglement in 1 second, entanglement which is higher than this 1/100, right? And nice, it really shows you how weak the gravity is. So after this time, the center of mass has moved by 10 picometers. And also it's important that we also looked into other, possibly entangling forces such as the Casimir force. And within this regime, it's 100 times smaller. So it will really be mainly gravitational entanglement that is obtained in such an experiment. How much time do I have actually? Mm-hmm.
No, even more.
Okay. Okay. And then I still say a few words about this. So in this experiment, so there are of course other usual sources of decoherence, right? And you want to make sure that this doesn't happen, right? So this entanglement really can survive. And recall that it takes 1 second to develop this observable entanglement, let's say. above 0.01. So in this limit, where we are actually in this limit, where the extension of the wave packet after cooling down is much smaller than the wavelength of thermal photons, and it turns out they are just irrelevant, right? So the decoherence times here are much, much bigger. But go ahead.
Why do you use spheres?
Oh, it's okay. I can repeat for everyone.
The question is, why do you use spheres? I mean, it's well known that if you use plates
would not be good. Because
why?
There are two of them, so I don't know how big plates, but plates have, in principle, have this gravitational field that is independent of the distance, right? So really a big plane would have a field which is distance independent. And you really need to have some gradient in order to entangle. You want to have different force on different parts of the wave packet of the second object. We actually did look into different shapes. We also
then are spheres the optimum choice?
Actually, it seems to be, yeah. We were also looking at rods, and spheres, looks like spheres is the object to go. It seems optimal, yeah.
So, sorry, Tommy, can I continue on the same?
Go ahead.
Because you said that this linear term contributes only to the phase, and you need a quadratic, and I think this refers now to your reply also to Anton. But is it because you want entanglement in external degree of freedom? Or like Bose et al., I think, and Chiara and Vedral, they have this entanglement.
Oh yeah, it could be in the phase, sure.
In the phase.
Like in the cow experiment, yeah.
Which is somehow then easier because it's kind of one order of magnitude.
Yeah, good point, yeah. So here we're really going for quadratic. Marcus also has at least quadratic.
But also in this case, the kind of phase that you accumulate has to have a position dependence. So it is actually, the coupling is exactly the same like in the free fall experiment. Because the spin only goes along with the center of mass motion in that case. So it is the coupling, again, the gravitational coupling to the center of mass motion that then accumulates a phase in the overall spin center of mass motion wave function. But the coupling that generates the phase is exactly the same like in Tomek's case. So you don't gain there. It's exactly equivalent.
Yeah, I think they have some, so Chiara and those guys, right? They have some papers where they also analyze this further decoherence parameters, and I think it might be a bit better from this perspective, a bit shorter, but nothing, not an order of magnitude. It still takes a second to accumulate this measurable entanglement. Yeah, so the other one is that we had a look at was this decoherence due to air molecules, and this one is more demanding. The Broglie wavelength is shorter, and it turns out that at this vacuum 10 to the 12 particles per cubic meter, it's actually a killer, right? It's short, it's 10 to the -4. But at space conditions, it is 40 seconds, so that would actually be, in principle, is an option, right? Okay, so that's all. We had some further analysis with the noises and stuff, but I really want to come back to, in this last minutes, back to concepts, because there is certain incompatibility. Maybe you could think it when you heard these two parts of the talk. So in the first one, I was actually arguing for this picture, right, where you have two masses that are coupled through another object, right, through gravity. But in the actual calculations used in the second part, I just use Newtonian potential, right? So is gravity mediated, right? One could ask. On macroscopic scales, it is, I suppose, right? Because we have, for example, these black hole mergers that show that the gravitational waves move with the speed of light. Retardation are the strong experimental evidence for mediator, that gravity is mediated, and we could probably think that this is a good picture. So since it is on the macro scales, likely it is also on the micro scales, but I don't think there is any experiment between two spheres that are like micron apart or even a millimeter that would be able to detect this kind of retardation. So somehow, in a sense, you could think that both of them are correct. This one is kind of on a bigger scale, but effectively, Newtonian picture is probably really giving you the right numbers when you're talking about things that are very, very nearby, are small, and they don't move fast, non-relativistic masses. But actually, in any case, even if you are this kind of maybe pre-field theory Newtonian physicist, right? I think these gravitational experiments would also be valuable to such people. And so here's why, right? Because even in this direct coupling, as I was arguing, you have to go to the second order term. So it really detects the presence of at least the second order term in your expansion of gravitational potential. So it's kind of like a precision test, right? So how many orders do I actually have to use to explain this stuff in the expansion of gravitational potential to explain the stuff I observe in the lab? And entanglement shows you that you have to have at least the second order. And actually, it turns out that there is a really simple check for the third order term. So I'm talking about this expansion where I had displacements divided by L. And it turns out that, so actually something for experimentalists, right? Once you somehow do these experiments where you observe gravitational entanglement, try pushing these masses towards each other. It actually turns out that if you push the masses, then depending on your initial momentum, there is no entanglement does not depend on initial momentum if your potential is up to quadratic, and it does depend when it's cubic and so on. So it really, if you see momentum dependence in entanglement, initial momentum dependence, it is a witness of a cubic term. So really a simple modification of that one and further order of magnitude. You prove, that next order of magnitude is relevant. So precision test essentially. And if you think about gravity if you think about these experiments in this mediator thing, then I already argued that entanglement gain with suitable, or if you can prove that entanglement is greater than the sum of initial entropies, then you have a witness of quantum coherence on this C if you embed in quantum formalism the description of such experiment. So altogether, a question emerges. Is there any way that we can verify the presence of mediators or absence for particles that are really nearby? You can't do this with just retardation. So they are too close. The speed of light is too high. So can you do it in another way? Actually, I don't know, right? This is just a question, but I think I have one last thing to tell you about a protocol which will show you that there was no mediator. I think you can actually witness the absence of mediators in principle. And it's just a toy argument. Maybe, let's chat and develop this. So imagine you have two particles that start in some state and evolve under some Hamiltonian. You end up in a state, some rho AB state at time t. The question is, can I understand the very same dynamics by adding an object in between, some C object with whatever initial state, but the Hamiltonian that splits in this form? So this evolves somehow at time t, and I want, after tracing out this mediator, I want to have exactly the same dynamics as the one with which I started. And here's the toy example that sometimes it's definitely impossible, at least on a piece of paper. Namely, imagine that this is a pure product state, and this thing is something that entangles. And it's done, on a piece of paper, the system is pure at all times. So that's the toy and kind of unrealistic part of it. So because it's pure, it would require the mediator, which is at all times completely in a product state. And so, for example, by using this fact that entanglement, okay, and then you can prove that there is no way entanglement can grow in such a setting. So why is this a toy model? And I encourage you to think about this more. One, of course, in real labs, this is never a pure state. There will be some mixedness involved. But the second one is that it's also, what I said here, it's on a piece of paper because I said that the state is pure at all times. That's something also that you cannot verify, really. You can only measure it at some finite time instances, but still, perhaps it is possible to derive some inequality that will, in principle, show that certain dynamics cannot be mediated. Okay, so let's conclude. It is possible to entangle two objects via classical mediator, but you have to have initial entanglement, and still it's interesting that you can localize it via classical mediator, right? It's somehow this entanglement, it was like this, that entanglement between A and two other guys could be localized into AB while keeping this C classical, mediator classical. I also showed you a method for revealing non-classicality of mediator from observation of the probes only by making minimalistic assumptions about this mediator. And when we apply that to gravitational coupling, it seems to me that the most user-friendly experiment in showing this gravitational entanglement would be in space, right? Essentially. Yeah, maybe we can maybe we can design methods or, for to do in some less official having beer gardens of this conference. Maybe we can design methods to detect lack of mediators. Okay, I should say that I'm supported by this NAV. Thanks a lot. Time for questions.
Thank you, Tomek. Time for questions. Czesław?
I'm coming back to my question and remark. I don't know about experimental requirements, but it seems to me that really what you have in the Bose et al. And Marletto-Vedral paper is, as you said, is entanglement in the phases. Basically, this is nothing else than cow experiment when the source of gravitation is quantum in a superposition. And therefore, it seems that only linear in potential term is relevant and not quadratic, which seems to be, in that sense, order of magnitude in your expansion easier to achieve.
I think so. The hard part of this one is that you have to prepare this superposition, which is, in that case, it's a quarter of millimeter size if you want to have gravity dominate.
You need interferometric, yeah.
So this is the starting point will be really difficult to actually do. Yeah, but I think so. It's like cow.
Okay, more questions?
Well, a general question on this idea of the mediator. So suppose you can certify that there was a mediator there. How would you ever know its gravity? I mean, by this, you couldn't, right? Okay, just to make sure I got this right. Yeah.
So this is very important. So in actual experiments, you will probably have other fields. I don't know. If you have also electromagnetic fields and so on, and you, by other means, you have to argue that somehow gravity is dominating this entanglement generation.
This is should probably go to Marcus at the back rather than you. You talked about releasing the spheres. Do you think it's at all possible to only release them horizontally and keep them trapped vertically so that you don't have to go to a drop tower?
Well, you have, okay, so Marcus will answer. Huh? Go ahead.
Definitely.
And what do you think about doing this in space?
Okay, so if you can do it in a vacuum chamber sealed cryogenically, that without any freefall requirements, if you can do it in trap, why go to space?
Right, but
I can even have better boundary conditions, a better experimental environment, not going to space. Today you find, for example, in the A-trap experiments, these are panning traps from Klaus Blaum's group. You get vacuum levels on the somewhere at 10 to the minus 17 millibars at cryogenic temperature, so that outperforms any space environment.
Yeah, fair enough. But I think really somehow in these calculations, I think this intuition that you actually need a wave packet that spreads is important, right? So if you have a trap,
right? But if you substitute free fall with free dynamics, you have exactly what Gregor said. You keep a particle just stably, switch the trap off, and then you just have free dynamics of the wave packet. It evolves freely without falling. So just kill the fall, and you win a lot of space.
Okay.
And you don't win time, but you win space, definitely, and money.
Okay.
We have Anton here.
That's an interesting option.
Your model reminds me a little of Planck's original explanation of the black body radiation. Because what he assumed was, he didn't assume anything about the field, or the light field. He only assumed that the energy is quantized. The exchange, the interaction between the field and the walls is quantized. It sounds a little bit like what you are doing. I have another question. Can you translate your model of the mediator and so on to me into the picture of gravity in GR, that gravity is not a field, but as we know, a feature of space-time and so on and so on.
Right. So I haven't thought about this one, but the experiments at the very beginning, which require general relativity, so this one's, these ones actually always use also just one fixed space-time. So I guess for this one you could cook up some model where you know it's probably very simple, but in general, I don't know, nice program.
Okay, we have more time for questions.
Not a question, but one quick comment. So you said low frequency oscillators need to cool down. Looks bad, but LIGO seems to have cooled down to 10, n equals 10. It's actually a bit worse than that because it's not at half hertz. They shift the frequency electrostatically to up to 100 hertz. So they oscillate their mirrors at 100 hertz and then cool it down to occupation number of 10. So it's a bit less optimistic than that.
Yeah,
just a note.
Fair enough, thanks. I really think this is probably not the way to go. Right? It's more like the second step. You really have to allow this expansion.
Okay, we have one question from online participants.
Yes.
Right?
Can you hear me? Does that work?
Go ahead.
Does that work? Can you hear me?
Yes.
Oh, amazing. Yeah, well, actually, I think it's, I'm coming back to also Marcus' point. I was imagining whether you could trade the free fall for some flat, some flat table on which you have your mass orbiting, and this table is perpendicular to the gravitational field and has no friction. And then you kind of kick your two masses and let them interact gravitationally. Would that replace the free fall?
Yeah, probably. But how do you keep them?
Yeah, well, there is a trap, right? But the trap just prevents them from falling. But in the other dimension...
I see. So essentially you open the trap.
Yes.
Yes, that's an option, I think. Yes. The opening the trap is definitely an option. You don't allow them to fall down, but just to interact within the plane, yeah. Yeah, actually, opening the trap is probably something that a concrete calculation one could try here, yeah.
Okay, good. So we have still more time for questions. Okay, I have one question, perhaps naive. It's a bit too much of quantum in all calculations. So have you been thinking, can you put this in some kind of device-independent scenario? Would this do?
I think this is actually, good point. And John Selby has a paper on that. So, oh yeah, actually he's here, wait. Yeah, John, can you say, I think you have something, right, about this, exactly this mediator stuff, where you actually have some post quantum theories for the mediator.
So could you repeat the question again?
Yeah, my question was, this is all about quantum formalism and entanglement. Yeah. Is there a way to talk about these things, mediators in device-independent setting?
So you can embed it all within the generalized probabilistic theory formalism and then prove sort of similar results there. It's not sort of fully device-independent, but it's a long way there, I think. And then you can sort of look for post-quantum theories that can generate this sort of entanglement between things as well.
Okay, good, thanks.
So, yeah. Essentially, you have, just to sum up, if I got that one right, it's two quantum objects coupled via post-quantum mediator. Yeah?
Yep, or two post-quantum things with a post-quantum mediator as well. You can sort of choose which bits are quantum and which bits are post-quantum.
Okay, good. I think it's time to
Just
stop.
also,
Yeah, sorry. Do you want to comment?
No, thank you.
Let's thank Tomek. Thank you.